it's time for another Lagrangian mechanics problem. Someone suggested this. I made up a name for it, the swinging Atwood machine. It may be a legitimate problem from other things, but I've never done this one before. So an Atwood machine has two masses connected by a string over a pulley. So in this one, what I have is this mass is pulled off to the side. Okay, so this mass can move up and down. This mass can move this way and up and down. Let's do it. Okay, so we're going to use the Lagrangian mechanics. Why? Because of forces of constraint. So in this case, I have this tension here. I have a tension here. It changes direction, changes magnitude. There's just no way to really get the forces on these things with that tension. I mean, there is a way. I take that back. There's a way, okay. But it's not very easy. Instead, if I use generalized coordinates to describe the system, I can use the Lagrangian, which is kinetic energy minus potential energy, and I can use Euler-Lagrange equation to find the equations of motion. So this says the partial of the Lagrangian L with respect to one of the variables minus the time derivative of the partial derivative with respect to the velocity q dot, where we qi, there can be more than one. So qi dot, the dot notation, I write this all the time, is the derivative of qi with respect to t. Okay. That's equal to 0. So that can give us an equation of motion. Yeah. So let's the first thing you want to think about is, how many degrees of freedom do I have in this situation? This one clearly has 2 coordinates and that one has 1. But if this one moves down, then the coordinates of this one are going to change too, right? So I have a constraint in there that the length between these two has to be constant. So let's just pick 3. I'm gonna pick 3 variables, and then I'm gonna constrain it to 2. Okay. So let's call this y equals 0 up here. So let's call this y. I'm gonna use a positive value y. Y is a positive number. It's the length of the string. So this would have a negative a gravitational potential. That's kind of stupid, but I'm gonna do it anyway. And let's call this length r, and then we'll use that angle theta. So I have 3 variables there. But now I'm going to say, and let's assume that my pulley is infinitely small. Because actually, if the pulley has some size, there is something weird that can happen, and I don't want to deal with that. So this is a super tiny pulley, and I'll show you that later. So that means that, let's call the whole length of this some constant. Then I could say y plus r equals some constant. Okay, so that's a constraint equation, and I'm going to use that. And actually, let's go ahead and say r equals c minus y. So I have 3 variables that I can use to describe the system, but then I have an equation of constraint too. So I have y, theta, and r. Okay, let's go with that. Now I need to find the kinetic energy. So let's start with mass 1. That's pretty easy. T1, the kinetic energy for 1, is going to be 1/2 m1 y dot squared, right? Because y is a Cartesian coordinate, so I can write the kinetic energy. I can write the derivative very easily. It's very easy to do. This one, not so easy to do because it can move this way and it can move this way. So what I want to do is to get the x, y, the Cartesian coordinates of mass 2 in terms of r, theta, and y. So let's do that. So if this is my origin, then I can say x2, the x2 value of this is going to be equal to the hypotenuse r, and this is going to be the opposite side. So it's actually going to be equal to negative r sine theta, right? Because it's in the negative x direction, just the way I drew it. And then I can say y2 is going to be equal to negative r cosine theta. Now I can write the kinetic energy T2 as 1/2 m2 x2 dot squared plus y2 dot squared. So those are in Cartesian coordinates, that is the kinetic energy. So now I can just take the derivatives of these two with respect to time and then square them and plug them in here. So let's take the derivative of x2. x2 dot. Okay, so I have r and theta. Both of those change with time. So let's take the derivative of r. I get negative r dot sine theta. Now I have to take the derivative of theta because it changes with time too. So the derivative of sine theta is going to be equal to cosine theta. Then I have to take the derivative of theta, so I have theta dot. So I'm going to get minus r theta dot cosine theta. Now let's do the same thing for y2. y2 dot is going to be equal to negative r dot cosine theta. And then I'm going to have to take the derivative of cosine theta, which is negative sine theta. So I'm going to get plus r theta dot sine theta. Now, I really want to get these in terms of y's. So I can do that, and just I will in a second. But up here, if I do r dot, because I don't really care about r, right? So I want y. So r dot is just going to be the derivative of this, which is negative y dot, right? Because the derivative of c is constant. So that's going to be something I can substitute in later. Okay, so now let's go ahead and square these two and add them together. So if I square this, I get x2 dot squared. I'm going to get three terms. I get r dot squared sine squared theta. I get a cross term, which is going to be plus 2r r dot theta dot cosine theta sine theta. And then I'm going to get that term, so I get plus r squared theta dot squared cosine squared theta. And then if I do the same thing for y2 dot squared, I'm going to get this squared, so r dot squared cosine squared theta plus, minus 2r r dot theta dot cosine theta sine theta. You see something beautiful there. Plus r squared theta dot squared sine squared theta. So when I add these two terms together, I'm going to get r dot squared sine squared cosine squared, so it's just going to be r dot squared. These two terms cancel, and then these two terms again, I get a cosine squared plus sine squared. So that means T2 is going to be equal to 1/2 m2 times r dot squared plus r squared theta dot squared. And if you said, hey, that's just the kinetic energy and polar coordinates, you are correct. But still. Okay, so let's we need to do one more thing. We need to do the potential energy, right? So I'm going to say U is going to be equal to M1 G Y negative, right? It's the negative, because I called Y a positive number, and I don't know why I did that. Minus the Y value for M2, which is going to be minus M2 G R cosine theta. And then I can put that in, so let's, and then here's my, let's just put it all together. Okay, so now I have L is 1/2 M1 Y dot squared plus 1/2 M2 R dot squared plus R squared theta dot squared. And then I have minus the potential, so it's going to be plus M1 G Y plus M2 G R cosine theta. Now I do want to get that. I do want to get that all in terms of theta and y. So remember, R equals C minus y. R dot equals negative y dot. So if I put those in here, I get, is that what I want to do? That's what I want to do. L equals 1/2 M1 Y dot squared plus 1/2 M2 R dot squared is just going to be negative, it's going to be negative y dot squared, so this is going to be y dot squared plus, I'm just going to leave this as C minus y squared, and then theta dot squared, and then I have one more right there, plus M1G Y, that's a y, plus M2G C minus y, that's R, cosine theta. So that's my Lagrangian. Okay, now I can start doing my Euler-Lagrange equation. So let's start with the y's, right? I have two of them. I have one for y and one for theta. So I'm going to say the partial of L with respect to y. I need to do that first. So let's go through here and where are my y's? I'm looking for y. Here's a y. So I need to take the partial with respect to y. So I have 1/2 m this times that. If I take the partial, I can use the power rule. I'm going to bring the 2 down, and I get m2 times c minus y to the positive theta dot squared. And then I need to take the derivative of the inside, so I get a negative sign, because the derivative of c minus y is -1. Okay, now I have another term right here, so I just get a plus m1g. And then over here, I'm going to get a minus m2g cosine theta. I think that's right. Check. Yeah. Okay. Now I'm going to take the partial with respect to y dot, partial of L with respect to y dot equals. Okay, so here's a y dot, so I get m1 y dot. Here's another y dot. I get to the 2's cancel. I get another 2 cancel. So I get plus m2 y dot. Looking for y dots. That's it. Okay. So now I'm going to take the derivative of this with respect to time. d dt partial of L with respect to y dot is going to be m1 y double dot plus m2 y double dot, or m1 plus m2 y double dot. And so this minus that has to be equal to 0, so this is equal to that. So let's write that out as m1 plus m2 y double dot equals this whole thing, negative m2 c minus y theta dot squared plus m1g minus m2g cosine theta. Now I'm going to go ahead and solve this for y double dot. That actually turns out to be important. So I'm going to say y double dot, let's divide both sides by that. Negative m2 c minus y theta dot squared plus m1g, that's a g, minus m2g g cosine theta, all of that over m1 plus m2. And that gets a box. My pen's getting a little weak. Okay, so now I can use this again, and we can do the same thing for theta. So the partial of L with respect to theta is equal to, okay, looking for thetas. That's a theta dot, doesn't count. That's the only one right there. So the partial of this with respect to theta is going to be equal to negative m2 g c minus y sine theta. That's it. That's a c. I'm sometimes messy, and I apologize. Okay, now let's take the partial of this with respect to theta dot. The partial of L with respect to theta dot. So I'm going to look through here for theta dots. Here's one. So I'm going to have a power rule, bring the 2 down. I have to multiply by this. So I get m2 c minus y quantity squared theta dot. Looking for another one. That's it. So now I need to take the derivative of this with respect to time, d dt partial of L with respect to theta dot is going to be equal to, now I do have 2 terms here, right? Now this is a derivative. This is not a partial. So y depends on time and theta depends on time. Let's do the theta first. That's going to be m2 c minus y quantity squared theta double dot. Then I have to take the derivative of this. I'm going to use the power rule, so I get a 2 m2 c minus y theta dot. And now I need to take the derivative of the inside, which is going to be negative y dot. So I get negative, see, I knew that was coming, negative y dot. And so again, this has to be equal to that. So let's set that equal. I get m2 c parentheses c minus y quantity squared theta double dot minus 2 m2 c minus y theta dot y dot equals this minus m2 g c minus y sine theta. Okay. Again, I want to solve this for theta double dot. So let's get this for theta double dot. I'm going to add that term to both sides. So I get m2 c minus y quantity squared theta double dot equals 2 m2 c minus y theta dot y dot minus m2 g c minus y sine theta. And then if I divide both sides by that, I get theta double dot equals 2 m2 c minus y theta dot y dot minus m2 g c minus y sine theta. Almost there, people. Just hang on. Almost on target. Stay on target. M2 c minus y squared. And that is theta double dot. Okay. So we have theta double dot and we have y double dot. But, I mean, do you want me to solve that differential equation? You can say, yes, I want you to solve that differential equation. But this differential equation has theta dot and y dot in it, right? And theta. And then my other differential equation, which is right there, I want to show them both. Let's just fold this over. This is the power of paper, right? Can't do that on a computer. Okay. So there I have, and y double dot depends on theta dot, depends on theta. So it's not trivial. So we can still do this. We can still do this because we'll just make a numerical solution, right? So here's the idea. I'm going to move that aside because it's folded. So I have theta double dot as a function. So we're going to do a numerical solution, and so that means I'm going to say delta t equals 0.01. I'm going to break this into 0.01 seconds. During that time, I'm going to assume I can calculate theta double dot, which, guess what? I can, right? If I know all my initial velocities, theta dot, y dot, if I know my initial theta and y, I can calculate this. So I can get an expression for this. And now I'm going to assume during this time interval that it's constant. So this is going to be delta theta dot delta t. That's theta double dot is, if it's constant, it's the change in velocity with respect to time. So this is going to be equal to theta 2 dot minus theta 1 dot over delta t. That's the velocity at the end of the time interval. That's the velocity at the beginning, which I need to know that. Now I can solve for this. So I get theta 2 dot equals theta 1 dot plus theta double dot, which I just calculated, delta t. So now I have the velocity at the end of the time interval, the angular velocity. I can do the same thing by assuming this is constant. I can say theta 2 dot is going to be equal to delta theta over delta t, and that's theta 2 minus theta 1 over delta t, or theta 2 is theta 1 plus theta 2 dot, because I just calculated that, delta t. Important. Calculate theta. So calculate theta, use that to find the theta dot at the end of the time interval, use that to find theta at the end of the time interval, and then I can go up again. But I got to do the same thing for y, so I'm going to have to say y double dot equals, I can calculate that, y2 dot is y1 dot plus y double dot delta t, y2 equals y1 plus y2 dot delta t. So now I can calculate my y's at the end of that time interval and just do another time interval. Do it again and again and again. And that's what I'm going to do. And I already did it. I was going to program this for you, but I was afraid I'd make a mistake. So it's already programmed. I'm going to give you the code, but I'm going to go over everything here. So let's switch over here to the computer. Okay, so here we are. Okay, let me make this bigger. I want it big, really big. There we go. Okay, so this is Python. I'm actually using GlowScript Web vPython that has a lot of different names. So I just have my constants here. I have G. These are my two masses. This is the radius of my cylinder for my pulley, just because I'm going to draw it. That's my pulley. It's just a cylinder. So in Web vPython, we can make three-dimensional objects. I made these in 3D. This C I don't really need, but I put it in there anyway. That's just the top part of the pulley for the length. And then this is the total length of the string, right? Because I have a mass hanging down here. I have a mass over here. I got to go over that pulley. So I set that to the total length, LT. here's my initial theta. And these M1 start, M2 starts, they're the points on the edge of the pulley so that I can draw the Cartesian coordinates from there. Because in the problem over here, I assume they both started kind of at 0 with the 0 size pulley. So M1 is actually a sphere, M2 is a sphere in 3 dimensions, and then I have a cylinder to represent the string to hang them down, just because. So that's not super important. If you want to get better at drawing these things, we can do that later. So down here, this is important. I start with time, t equals 0, my time step of 0.01. I need to know my initial velocity. If I want to update the position, if I want to update the velocity, I need to know the velocity at the beginning of the time interval. So I have to know the initial conditions, both position and velocity for both variables. And that's what it is right here. I already have theta up here. So that's theta, y. I have y too. Okay, so I have y theta, theta dot, y dot. After that, it's just golden here. This line right here, line 30, that's my equation that I solved for y dot. That's the same thing. Okay. Now you did be careful, just a quick note. M2 is the scalar mass of each thing. M2 is the sphere, it's an object. So I had to have them have different names. But I just calculate out the whole thing. Here I have LT minus C just because of the way I defined LT minus C is my C in my paper. So, and then I calculate my theta double dot. That's that equation I solved for. So I had those two equations I got. Those are the two equations right there. Now, right here in line 32, I update the y velocity, then I update the theta velocity, I update y, I update theta. I'm done. Now I just need to move my little pieces around. So this line moves the position of the three-dimensional sphere. This moves the line. I recalculate. I want to do it in terms of r, so I calculated r instead of y. I don't want to deal with y. And then I draw mass 2. I move mass 2. I move its line. Update time. That's it. Okay, let's run it. It should run because I already ran this. So you'll notice that if I have the masses exactly the same, if this one's swinging down, then the tension is going to be greater than the other mass, and it'd actually go up, right? So it would swing all the way down. But I put the cyan mass is a little bit more massive. So when it swings down, when it gets to the edge, the tension decreases because it's not accelerating, so it moves this way. So you get this like up and down thing. I think this is the way it should be. It is in 3 dimensions. I just want to show you that because that is pretty cool. And then, another thing that you could try is, well, what if theta is equal to 0? If I have them like that, then it should just be a plain Atwood machine. So let's put this at a short time, and then put initial theta as 0 times that, and then we can see if that runs. And this line right there, they're both leaving a trail. So that seems to be correct. I mean, we could plot the position as a function of time, but it seems to be working. So I'm pretty happy with that. You could also give it an initial velocity if you wanted to, angular velocity, whatever. Let's just try, I didn't try this. Let's try something crazy like 60. Okay, so this one, I think it's going to crash. I think it's going to crash because what's happening is the tension is going to be too great because it swung down too far and it's going to pull it all the way up. Let's run it for a little bit longer and let's just see. Let's say 2.5 seconds. It's going to keep calculating. It don't care. Yeah, see, it's just going to keep on moving that value up. Let's see if we can, if I make the mass much less. Let's make this mass 1 at 0.1. Let's see what happens there. Oh, I didn't expect that. I don't know if that's realistic, but just make it. There we go. Okay. I'm pretty happy. I don't know for certain that it's correct. I assume that it is, but I think it's at least on the right track. I always make mistakes. Okay, maybe I make those mistakes on purpose for you to find them, but I do make mistakes. The general idea is legit. If you get the second derivatives of both of the variables, then you can make a numerical calculation. That's one way to solve these differential equations. Okay, so again, I'll have that code down below. Hope that helps. I'll talk to you later.